Amid the majestic Alps, where steep peaks are covered with snow all year round, the Swiss have carved deep inside massive mountains to build an ambitious energy project almost entirely underground, known as the Mandarin hydropower plant. Behind this gigantic project lies an extremely complex construction process, drilling long tunnels through solid rock, transporting equipment weighing hundreds of tons along narrow mountain roads, and installing the entire power generation system inside enormous underground chambers carved deep into the mountain. Thousands of engineers, workers, heavy machines, and hundreds of millions of euros in investment were mobilized to create one of the most advanced hydropower systems in Europe. So how do you build a power plant deep inside a mountain at an altitude of thousands of meters? Join Mandarin Tech to find out. The Pumpspeicherwerk Mandarin hydropower plant is located in the Linthal Valley in the canton of Glarus, Switzerland, one of the most rugged high mountain regions of the Alps. The facility was designed as a massive pumped storage hydropower system built deep inside the mountain between two alpine lakes. Lake Mutsi, situated at an elevation of more than 2,400 meters, and Lake Limmerboden below, with a vertical height difference of about 630 meters. This enormous elevation gap effectively turns the entire mountain into a natural energy battery. With a generating capacity of up to 1,000 megawatts and a total investment of more than 2.3 billion US dollars, construction of the project began in 2008 and was completed in 2016 after nearly 8 years of work. At the peak of construction, more than 1,000 engineers and workers operated continuously in the Alps, using tunnel boring machines, drilling and blasting systems, construction cableways, and heavy transport equipment to build the underground facility. The total volume of rock excavated from the mountain was so enormous that the underground space created could fit around 30 football fields, effectively transforming the entire mountain into a vast engineering complex hidden beneath the Alpine rock. Before construction could even begin, the Mandarin project had to solve a massive challenge: transporting an entire construction site into the middle of the Alps. At an altitude of over 2,000 meters, the location was almost completely isolated from the world below, surrounded only by rock, snow, and steep mountain slopes. To solve this, engineers built a construction cableway system stretching across deep mountain cliffs, allowing heavy machinery and specialized construction equipment weighing dozens of tons to be transported to the site along a 4-kilometer cable line. Even the workers had to fly to the site. In many places where no roads existed, helicopters were used to transport them onto the mountainsides, while dropping them into work zones like climbers descending from the sky. Only after this extraordinary logistics network was operating smoothly could the Mandarin construction site begin its next phase, drilling deep into the heart of the Alpine mountains. Because most of the Pumpspeicherwerk Mandarin facility is built deep inside the Alps, and the granite here is far too hard to excavate quickly with conventional machines, engineers had to rely on controlled drilling and blasting to open a path into the mountain. The process begins with hydraulic tunnel drilling rigs. Long drilling arms, several meters in length, are pressed directly into the rock face, creating dozens of boreholes that range from a few meters to more than 10 meters deep. Each hole is positioned according to a carefully calculated pattern to control exactly how the rock will fracture. Once drilling is completed, workers begin loading explosives into each borehole. The explosives are placed in layers, separated by stemming material to ensure the blast energy is directed into breaking the rock rather than escaping outward. Then, an electronic detonator system is then connected to every hole, allowing the charges to be triggered in sequence with delays measured in milliseconds. When the area is cleared and the system is activated, dozens of explosive charges detonate in a precisely timed sequence, cracking through meters-thick rock and gradually carving a path deeper into the heart of the mountain. Only through repeated blasting like this were engineers able to carve their way deep into the Alps. After each explosion, the broken rock was gathered and quickly loaded onto construction trucks, then continuously transported out of the tunnel in constant cycles. Through hundreds of these drilling and blasting rounds, engineers gradually created a tunnel network stretching more than 20 kilometers, along with enormous underground chambers inside the mountain. One of the largest spaces is the main turbine hall, about 120 meters long and nearly 50 meters high, roughly the size of a multi-story building carved directly into the solid granite. The entire underground cavern was excavated to a length of 125 meters, a width of 25 meters, and a height of 35 meters. To create this enormous space inside the mountain, about 315,000 tons of rock were removed from the Alps. By February 2016, the final blocks of rock were blasted away, marking the moment when the cavern inside the mountain reached its maximum size. After a long period of working deep inside the mountain, the miners proudly celebrated the achievement of their work. Immediately after the excavation work was completed, the concrete foundation construction began. These foundations would later have to support the entire weight of the enormous and extremely heavy machines inside the power plant. For this reason, the reinforcement steel framework was designed and installed on a very large scale. In total, there were about 750 different concrete pours within the underground cavern, all of which had to be completed in just over a year. At the same time, work inside the powerhouse cavern moved to building the upper structures. Concrete columns supporting the overhead crane rails were constructed so that massive machinery could later be transported and installed. Using large mobile cranes, engineers first assembled the formwork for the crane rail columns and beams. Once completed, concrete was poured from above, gradually forming the load-bearing structures for the crane system inside the cavern. In early 2012, the excavation of the massive machine cavern, about 50 meters high, was completed. From that point on, the project moved into the phase of finishing the interior. Construction progress was extremely tight, so work was carried out simultaneously in multiple areas. In the foundations, the suction pipes for the pump turbines began to be installed. At the same time, the side walls of the powerhouse cavern were cast in concrete. The arched roof above had previously been supported mainly by the mountain's natural rock. Once the concrete layers were completed, the structure formed a closed ring, allowing the cavern to withstand the enormous pressure from the surrounding rock mass. Inside the machine shafts, directly above the suction pipes already embedded in concrete, engineers continued pouring the foundations for the generating units. In total, more than 80,000 cubic meters of concrete were used in these underground chambers, enough to build roughly 700 family homes. To connect the power plant to the grid, high-voltage power cables were routed through an access tunnel to the substation in Tierfed. From there, a new 380 kilovolt transmission line was built across the Linthal Valley. This 17-kilometer line became part of Switzerland's extra high-voltage power network. To construct it, a total of 53 new transmission towers were erected. Some of these towers reach heights of up to 89 meters, making the construction process extremely complex. In the steep Rocky Mountain terrain, much of the construction material had to be transported to the installation sites by helicopter. At the same time that the power line was being completed, another crucial logistical task was taking place in the valley below, transporting heavy equipment into the mountain. Some machine components, such as the spiral casings of the pump turbines, were far too large to pass through ordinary tunnels. The heaviest equipment, including the generator transformers, weighed up to 190 tons, far beyond the capacity of standard transport vehicles. As a result, these massive components were delivered directly into the powerhouse cavern through the newly completed access tunnel. This tunnel was specially designed with large dimensions and equipped with a 200-ton transport cable system, allowing heavy equipment to be moved deep into the mountain. After the equipment was delivered inside, the installation of the generating units began. The spiral casings of the turbines were installed first. These massive steel structures must withstand the full force of high-pressure water flowing from the pressure shafts, so they are completely embedded in concrete. At this exact location, the pump turbine runner will later rotate at extremely high speed. Above the turbine, the main bearings for the turbine shaft and generator shaft are installed. Meanwhile, the moving components of the generator motor are also being manufactured and assembled in parallel. The generator rotors weigh about 330 tons, far too heavy to be transported as a single piece through the cableway system. As a result, they had to be assembled directly inside the powerhouse cavern. At the same time, the stator, the stationary part of the generator, was installed above the turbine. Once assembly was completed, the rotor was carefully lowered into the stator. During operation, the rotor rotates at about 8 revolutions per second, generating power equivalent to roughly 3,000 cars running at the same time. In November 2015, the first 2 generating units were fully installed. Shortly afterward, the first unit was successfully synchronized with the national power grid, marking an important milestone for the project. At the same time as the powerhouse cavern was being constructed, the pressure shafts carrying water from Lake Mutsi were also built. These shafts were excavated using tunnel boring machines, starting from launch chambers inside the mountain. They descend at an angle of about 40 degrees and end at the valve chamber, located roughly 600 meters higher. In this area, engineers also constructed the upstream pressure tunnel and a surge shaft, a vertical open shaft designed to balance water pressure within the system. From the valve chamber, the steel liners used to reinforce the pressure shafts were transported downward using temporary rail tracks. Moving and installing these steel pipes was extremely complex. Each pipe section was lowered piece by piece and then welded together inside the shaft, forming a continuous steel pipeline. In total, the steel lining of the pressure shafts reached a length of about 2 kilometers, and the installation process took roughly 3 years to complete. The steel lining for the pressure shafts was manufactured in a factory. From steel plates several centimeters thick, the metal sheets were rolled and bent to form giant steel pipes about 4.5 meters in diameter. Using specialized transport vehicles, the steel pipes were then delivered to the top of the pressure shaft. From there, they were slowly lowered down the shaft, which descends at an angle of about 48 degrees deep into the mountain. The entire pipeline system was installed along this pressure shaft. Near the bottom, it transitions into the distribution pipeline, beginning with a special section known as a Y-pipe. This structure splits the water flow into 2 branches, directing it toward 2 generating units. Because this area experiences the highest water pressure in the entire system, the pipe walls had to be several centimeters thick and welded together from multiple separate sections to ensure strength. Once fully assembled, all metal components were coated with a corrosion-resistant layer, protecting the pipeline from water exposure and long-term wear. Next comes the upstream pressure tunnel, which connects the valve chamber to Lake Mutsi. This tunnel has a diameter of about 8 meters, roughly the size of a road tunnel for cars, large enough to carry the enormous volume of water flowing through the system. At the tunnel entrance between 2012 and 2013, engineers constructed the Mutsi intake structure. When the reservoir is fully filled, the entire structure will lie completely beneath the water surface, leaving only the hidden water conveyance system running inside the rock of the Alps. From here, water flows through the pressure tunnel and down the pressure shafts to the turbines. On the powerhouse side, 2 downstream water tunnels were built to carry the water back to Lake Limmernsee. Once these tunnels and shafts were completed, the entire water conveyance system of the power plant was finished. Next came the construction of the water intake and outlet structures, which required Lake Limmernsee to be almost completely drained. Through these 2 structures, up to 200 cubic meters of water per second can flow through the system. Their hydraulic design was specially engineered to minimize turbulence and reduce energy losses. Above the lake, in the Oxenstafli area, a material processing center was built with rock silos and crushing machines. Rock excavated from the powerhouse cavern was processed here and later used as construction material for the Mutsi Dam. The material and equipment were then transported by a second construction cableway up to the Mutenalp area. This cableway was capable of lifting up to 30 tons per trip. The construction cableway continued to transport materials and equipment to the Mutsi Dam construction site. This site is located on the Mutenalp Plateau at an altitude of about 2,500 meters above sea level. Thanks to this cableway system, all machinery, materials, and heavy equipment could be transported from the valley up to the construction site in the mountains. The dam was built from 68 large concrete blocks, each about 15 meters wide. The entire dam wall was constructed over 3 consecutive summer seasons, taking advantage of the short periods of favorable weather in the high mountains. When completed, the dam measures about 1,000 meters in length and reaches a maximum height of around 36 meters, forming a massive wall holding back water in the middle of the Alps. After the dam was completed, the water level of Lake Mutsi could be raised by up to 30 meters. This increased the lake's storage capacity by roughly 3 times, creating a massive energy reserve for the pumped storage power plant. The scale of the construction site at this altitude was truly impressive. At peak times, up to 150 workers lived and worked in a dedicated construction camp built on the mountain. To support the work, a modern concrete plant was also built directly at the site, producing the concrete used for the dam. By 2012, about 1/4 of the dam had already been completed, and it was at that point that the enormous scale of the final structure began to clearly take shape. By the end of 2013, about 2/3 of the dam had been completed. 2 years later, in November 2015, the Mutsi Dam was officially finished. The dam was equipped with a crest walkway and highly sensitive monitoring instruments to continuously track the condition of the structure. In the summer of 2016, Lake Mutsi was filled for the first time, after all temporary construction facilities had been dismantled. Deep inside the underground caverns, the generating units gradually began entering operation. The pump turbines and motor generators can switch flexibly between pumping and generating modes within just a few minutes. At the control center in Tierfed, the entire system is continuously monitored, while the dispatch of the generating units is coordinated from Baden, depending on electricity market demand. After completion, the Mutsi Dam stands prominently on the Muttenalp Plateau, stretching more than 1,000 meters, the longest dam in Switzerland and also one of the highest elevation dams in Europe. It holds a massive volume of water used for flexible power generation, playing an important role in stabilizing the electrical grid and strengthening energy security in Switzerland and across Europe.